Welcome, everybody. Happy Thursday. So, let's see. Quick reminder, we have our second online exam tomorrow. It's online. Oh, that reminds me. I need to get back to work. I need to, finish your exam. Okay. Anyway, so I think that's the plan at least. So it will be available to you just as usual between 2 and 11:59 p.m. tomorrow. Apart from that, a week from tomorrow, we're going to have our second in-person exam. Okay. So it's going to be the same place, but I'll send you a reminder for that next week. All right. So before we get into chemistry, do we have any questions, concerns, comments, anything that I can try to clarify? Okay. Learning assistants, I see some blank screens. If you can unplug and plug them or something like that, that would be wonderful. Or maybe just try the power switch first. Thank you so much. Okay. So today we are going to wrap up unit 2 module 1. Only thing that we need to talk about is molecular spectroscopy, which will take about maximum 10 minutes, and then one question guaranteed on your next exam, maybe on tomorrow's exam as well. At least one question guaranteed, okay? Which is really simple. And then one example question would be what you're looking at on the screen. Can you answer a question like this? Okay. So by the end of today's lecture, by the end of next 10 minutes, you should be able to. Okay. So, and then that will gain you some points during your exams as well. Now, after that, we will begin Unit 2, Module 2. Unit 2, Module 2 is all about, mainly about using IR spectroscopy to identify the bonds in molecules, so that finally you will be able to determine what bonds we have in a molecule. Okay, number one. And then the second part of that will be about building up to the electron configurations. Okay, so we will not get into electron configurations today. I do not plan to do that. I will, however, finish IR spectroscopy part, and then and also give you a preview of coming attractions when it comes to something like atomic size or maybe ionization energies. That's it. Okay, that's going to be the goal for today. So mainly finish up unit 2, module 1, molecular spectroscopy, and talk about the bond, and then how to identify them using IR spectroscopy would be our learning objectives for today's class. All right. Now, with that, I'll give you a minute to think about this question at your tables, and then after that, we'll talk about this. Go ahead. Because I know that some of you have finished reading the reading assignment, the finished reading assignments last night, so you might be familiar with this already. But if not, that's okay. You will be by the end of today's lecture. Did I ask for the lowest or the highest? Oh, least energy. Okay. I might have messed up too because I came up with that pretty fast. That's okay. All right. So I'm going to close this question now, but I will come back to this in about 5 minutes. Okay. And these are our responses, which is pretty good. Yeah, let's talk about this. Now, we saw when we used so all this time we were dealing with atoms, like we were shining light at the hydrogen atom, and then we used the Bohr model to see how the electron jumped from one energy level to another energy level, and when they came back down it emitted photons and so forth. So we explained spectroscopy, absorption and emission spectroscopy using the Bohr model of the hydrogen atom. That's our foundation in understanding spectroscopy. Yeah. Now what we're going to do is we are going to bring that same knowledge into molecules, because in hydrogen atom what we saw was when it absorbed light, there are electrons jumping around. The same thing happens in molecules as well. Okay, the electrons electrons jump around, and then there are some other motions on top of electron jumping we can expect in molecules, and that's what we are going to be looking at today. Okay, so right now I'm exposing this is a molecule. Obviously, it has more than one atom. Okay, so it's happy, it's doing its own dancing thing. Okay, doing its own thing. So, but when I'm shining visible light at it, I don't see anything happening. And then if I move my cursor to UV light, does anybody have any guesses? What would happen? Oh, should we go to UV or IR first? UV means we are going up in energy, and IR means we are going down in energy. What do you want to do? Go down and come back up, or the other way around? What was that? Go down. Okay, let's go to IR. Okay, any predictions though? What's going to happen to the molecule if I go to IR? If I shine IR light at my molecule, some of you I know have read the textbook. Anybody who wants to tell me? Abby, anything? Okay. Millie, did you say something? Somebody? Oh yeah. One of these days, I promise I'm going to remember your name. So, okay, remind me your name one more time.
Oliver.
Oliver, go ahead.
Vibrational?
Vibrations, okay. All right, so let's see. All right, here's IR. Okay, let me do this one more time. Okay, so when I shine IR light at it, I can see that it induced bond vibration. See, it enhances the vibrational motion in the molecule. Okay, so in other words, IR radiation, okay, IR radiation induces vibrational motion in the molecule. Let's call it vibrations for the moment, or vibrational. Oh my goodness, I'll write it. Vibrational transitions or vibrational motions. I mean the same thing here. Are induced by IR. Okay. Now that's vibrations. What if I go down further to microwave? What do you expect? Ella? It's going to be rotational. Okay. Now, this is the same thing that is happening in your microwave ovens as well, by the way. Okay. So when you are exposing the molecules to microwave, wait for it, it needs to hit the molecule. There you go. Okay. So it is inducing rotational motions in the molecule. And I think I mentioned this before, in your microwave oven, it induces rotational motion of water molecules, and that is what is mainly giving rise to friction, and that gives rise to heat in, heating of your food. Okay. So yeah, so microwave radiation induces rotational motion. Let's write that down. Microwave, lesser energy now. Have a different call. Okay. No. I want to stick with this. Microwave radiation induces rotational motion. All right, one last thing left for us to do, that is UV and visible. Okay, we know visible is not doing anything. All right. Any guesses? What would UV do? Yes, miss. Yeah, it's electronic transition. That's the only transitions remaining now. Okay. So UV and visible light usually induce electronic transitions in matter. Like it happens with the atoms as well. You saw that with hydrogen atom. Okay. So here's what's going to happen. Let's see. Okay. Now, you notice that it actually broke a molecule. Now, what happened here was this UV radiation we shined at the molecule ejected an electron, moved an electron from a bond. So it made the bond unstable, therefore the bond broke. That's what happened here. And this is the same reason UV radiation can be dangerous to us. I mean, it can be carcinogenic. You know that, right? I mean, we have to avoid some UV radiation. And it's the same reason why we can use UV radiation to sanitize uh, uh, things, okay? Because they can destroy microorganisms by doing the same thing, because it can have this ionizing effect. Yeah, not as much as X-rays and gamma rays, but UV has some ionizing effects as well, because it affects electronic transitions. All right. Now, let me write that for the completion of our notes. So, UV, okay, we can write UV and visible. I'm going to call it UV vis. So, I mean, when you go to the lab, I mean, they might refer to as UV vis spectroscopy. Okay. So in UV or UV visible spectroscopy is also known as electronic spectroscopy for the same reason. Why? It induces electronic transitions. Electronic transitions. Oh, I want to say motions. Let's call it motions. Just to be consistent. All right. Now, we already know this. UV visible, out of these three types of three radiations we have categorized here, UV visible have the highest energy, okay, and then IR, and then microwave. Microwave has the lowest energy, meaning the rotational motions takes the least energy to be induced. In other words, so all of these, spectroscopy can be explained using quantization of energy, just like electronic energy levels are quantized. The vibrational energy levels and rotational energy levels are quantized as well. Okay, so when it comes to rotational energy levels, those energy gaps fall within the energy of microwave radiation, and that's why microwave radiation can induce rotational transitions. Okay, and when it comes to vibrational energy levels, those energy gaps between the vibrational energy levels falls within the IR radiation energy, infrared radiation energy. Okay, that's why infrared induces vibrational motion, and UV vis, like we have seen before, is going to fit into the electronic energy gaps. That's why it induces electronic transitions. Yeah, that is, we just connected what we talked about here to quantization of energy as well, at the same time. All right, that's it. We're done with Unit 2, Module 1. What questions, concerns, comments do we have at this moment? Ella, any questions? Okay. Any questions, concerns, comments? Okay. So now that we talked about this, let's go back. This is again summarizing what we talked about. The energy gaps for rotational falls within microwave, for vibrational energy gaps falls within infrared, and electronic excitations, and electronic energy levels falls within UV visible. We're talking energy gaps here, okay? And it's the same thing we just discussed before. Okay. All right. With that, let's finish this question. We go one more time. And then we'll move on to a brand new module, Unit 2, Module 2 in our textbook. Yeah. That's why it rotates. So they have different modes of rotations. So they have different energy levels, therefore. So microwave radiation fits in within these energy gaps. Therefore, when the microwave radiation hits the molecule, it excites the molecule so it can go to the other state, other mode of rotation.
Just that energy level just makes it rotate.
Yes,
Okay.
because
Yeah.
we'll talk about the same thing in IR region so that it make more sense. Yeah. All right. So I think That should be enough time for discussion. Therefore, I'm going to close this in 5. Actually, by 100%, I don't need to count. All right, wonderful. Least energy is required for the rotational, and the highest energy is for the electronic transitions. All right, do we have any questions, concerns, comments before we move on to Unit 2, Module 2? Okay, so let's do this. So in Unit 2, Module 2, the first thing we do is to understand bonds. We will understand what a bond is. Okay, and then we will learn how to identify bonds in a molecule using IR spectroscopy. That's it. That's the main main thing that we're going to be learning in the first half of Unit 2, Module 2. So just like anything that we are trying to explain, we will be using a model to explain the covalent bonding as well, okay, the bonding as well. And this model is called covalent bonding. So here's the idea here. If you think about any bond, how many atoms do we have in a bond? How many? Yeah, 2, always 2, okay? There cannot be any other number. In a bond, we have two atoms, okay? So we know atoms are made of a nuclei which have positive charges, and then we have the electron cloud around it. Now, if you have 2 atoms closer to each other, just like in a bond, okay, they should be repelling each other. Why? Because these nuclei have the same charges, same positive charge, okay? The positive charges repel, the same charges repel each other, okay? However, they are not repelled, they still stay together. Why? The electron cloud in between the 2 atoms are shielding or attracted to each other, attracted to each nuclei. As a result of that, it is held together by these electrons. So that's the basis of the covalent bonding model. Yes, we have repelling subatomic particles. There are repulsions. However, the electrons of one atom are attracted to the nucleus of the other atom and vice versa. And as a result of that, we have a stable arrangement of 2 atoms here in a thing called bond, covalent bond. Okay, so in a covalent bond, we have a higher electron density in between the 2 atoms, in other words, because that's what's holding the bond together. Those are called bonding electrons. All right, now I'm not done. I'm going to keep explaining this one more time, okay? So this is the idea of covalent bonding. Now what I want to do is I want to use a simulation to explain this one more time, if I can. All right, so here are 2 atoms. I don't know whether you can see on the screen properly. We have the blue nucleus in the center, and then we have the electron cloud around it. Do you see the electron cloud? Okay, wonderful. And then also, there is obnoxious red small particle moving around all the time. Okay, so what do you think that is? Yeah, that's an electron that actually try to depict the bonding electron that's going to participate in the bond formation. Okay, so what I'm going to do is I'm going to bring these atoms closer to each other. Okay, so they're attractive. Okay, so it's still attractive, and attraction grows to a certain point. Oh, no, it's too much. It's repelling. Oh, there you go. Okay, so when the attractions are balanced with the repulsions, that's where the optimum distance between the atoms occur. Okay, and then at that point, we say that we have a covalent bond form. And one thing that I want you to pay attention is, once the covalent bond is formed, we have a higher electron density between the 2 atoms. Okay, so that means, these electrons are shared between the 2 atoms. Now, another thing I want you to observe here is, due to the bond formation, these electrons are not restricted anymore. I'm going to use a different term that you will use in your exam, the upcoming exams, to gain points. Okay, so here are the technically correct terms that I want you to be using. I want you to get used to now. Okay, So now, before the bond formation, the bonding electrons, this is the key. I want you to pay close attention here. Before the bond formation, when we have the atoms like this, we say that our bonding electrons are localized to a given atom. Localized. Keyword localized. Okay. Just like you now, right? You are localized to this room. That is the same, it has the same meaning. I mean, no, but it's a fancy word. Maybe. All right. Now, after the bond formation, okay, let me show you. Oh, now here's after the bond formation, these electrons, the bonding electrons are not localized anymore. We say that the bonding electrons are delocalized between two atoms. If you do not want to write anything, okay, at least I want you to write one thing, the word delocalization. Let me write that for you too. Okay. It's not a bad idea to write that. So let's do this. Bond formation. Bond formation. I'm going to write this in uppercase letters so that, you know, because it's important. Bond formation, delocalized, delocalize bonding electrons between two atoms. Okay. This is the covalent bond, idea of covalent bond. Okay. Now, as a result of this delocalization of electrons, okay, you can imagine now, right? So try to imagine this with me. Initially, the electrons were localized. They had less space to move around. As a result of the bond formation, the electrons are delocalized between two atoms, meaning it has more space to move around. It's just like this, right? You are in the classroom now. Once this class is over, you can be between this classroom and then maybe the UA Mall or maybe the student union, right? Anywhere in between. So you're going to get delocalized between UA Mall and this classroom, or the student union and this classroom after the class is over. Okay. Just like that, after the bond formation, the bonding electrons are getting delocalized or spread out between two atoms. Okay. Now, I want you to think back to what we know about the electrons. Now, these electrons have more space to move around now. Now, what I want you to do is on your whiteboards, I want you to tell me, as a result of this covalent bond formation, okay, as a result of this delocalization of electrons between two atoms, what happens to the kinetic energy? Kinetic energy. And then what happens to the potential energy? E sub P. And then maybe total energy as well. All right. All right, go ahead on your whiteboards. Can you tell me what happens to kinetic energy, potential energy, and the total energy due to bond formation? And why? Especially why? Let's see. All right. So let's start with the kinetic energy. I know that most of you wrote the potential energy first, which is okay. Wonderful. Okay. When I walked around, I would say that. So let's think about the kinetic energy. Let's take a vote. Who says the kinetic energy of the electrons do not change due to bond formation? Nobody. Okay. Who says the kinetic energy of the electrons increase due to bond formation? Nobody. Okay. Nobody. Okay. Who says the kinetic energy of the electrons decrease due to bond formation? Okay, thank you. Why? Can someone tell me why? Yes, Sam. Yes, absolutely. Thank you, Sam. That's absolutely perfect. Yeah, we saw previously whenever the electron has more space to move around, it slows down. Therefore, the kinetic energy decreases. Okay, so kinetic energy decreases. Why? When we I wrote the same thing multiple times now, right? When electrons have more space, we're talking about the bonding electrons here, by the way, because the other electrons are getting somewhere else. Okay, when bonding electrons have more space, okay, they slow down. All right, if you write that, you're gonna get points. Yeah. Okay. Any questions about that? Any questions, concerns, comments? All right. Now, potential energy. All right. Who says potential energy does not change due to bond formation? I want you to think about this, please, with me. Okay. Nobody. Who says potential energy increases? I see a few hands for, okay, I've got a few hands for increasing. Who says the potential energy decreases? I see a few hands. What's the name? Say one more time. Shed, can you tell me why you expect the potential energy to decrease, Shed? Really, thank you. You know what? I agree. The potential energy decreases. I can come up with at least 3 reasons why, but let's hear from Shed. I mean, I'm boring. Shed, go ahead. Is it working?
Together, the attractive force increase, so potential energy decreases because of that.
Okay, so that's a good point. Okay, so during the bond formations, atoms are getting closer to each other. That means it is going to increase attractive interactions between them. Therefore, the potential energy decreases. Okay, that's what Shade said. Is there anything else? If you think about the electrons, is there anything else that we can think of why the potential energy must decrease? Ravita, do you have any idea? That's okay. That's okay. Uh, any other reason? So now let's think about this, okay? Bonding electrons were initially localized to a certain atom, okay? Meaning, so these bonding electrons were closer to other electrons of the atom because there are other electrons which we call as non-bonding electrons, okay? So bonding electrons and the non-bonding electrons were closer to each other. Now, if they are closer to each other, what can you tell me about the potential energy? So they are electrons being closer to other electrons. Therefore, the potential energy must be high or low. It should be high. Why? They are repelling each other. Repulsions means higher potential energy. Now, because of the bond formation, the bonding electrons go away from the other electrons. As a result of that, you have less repulsions between the electrons. Okay? Less repulsions means lower potential energy. Okay, so let's write that down. I mean, there are other reasons we can talk about if you want to. Okay, so at least one reason. How can we do it? Okay, there's more distance. Okay, there is more distance between the bonding and the non-bonding electrons. Electrons. Okay. Therefore, oh, I'm gonna write here. I'm gonna write 3 dots for the therefore just to save some space. Therefore, there are less repulsions. Therefore, there are less repulsions. Let's see. Okay. There are less repulsions. Okay. All right. Now, and apart from that, Shade mentioned about, when the atoms are closer to each other, they have more attractions. Therefore, there should be lower potential energy. Okay. And also, we can think about this. So when the bonding, so let's see if we can understand this. This is nice. You might be able to remember this too. Okay. So when the bonding electrons move away from an atom, the non-bonding electrons are gonna get closer to the nucleus. Yes? Can we wrap our mind around that? Okay. I'll give you an example. Okay. I know it's an answer is a no. Okay. I know that. Now let's think about this. Okay. Let's think of an atom as a mother with 5 children. Okay. So one child goes away to get married or something. Okay. So one child goes away and gets married. Okay. And what is going to happen to the other 4 children? They are going to feel the mother's love more now. They are going to get more attention, more pocket money, right? So the same thing happens with the non-bonding electrons. When the bonding electrons goes away, the remaining electrons are going to feel the mother's love. I'm sorry. The positive charge of the nucleus more. Yeah, as a result of that, there are more attractive interactions between the nuclei and the non-bonding electrons. Therefore, it's going to be a lower potential energy. Yeah. So that's another reason. That's another reason why the potential energy decreases when you form bonds. All right. Now the cool thing here is there's no doubt both potential energy. So both potential energy and the kinetic energy decreases, and there's no doubt the total energy must increase or decrease. Then decrease. Okay. The total energy, or let's say E total, must decrease. Why is what total energy is the sum of potential energy which decreases and the kinetic energy which also decreases. Therefore, the total energy must decrease. Okay. So any event that decreases the energy is stabilizing. And so bond formation is stabilizing. Okay. Why? It decreases the total energy. You can write that. Therefore, bond forming is stabilizing event. Is stabilizing. Okay. Why? It decreases the energy. Any event that decreases your energy is a stabilizing event. That's why bonds form. This is why bonds form. This is why two repelling like nuclei stay together, because overall it brings down the energy, and that's why the bonds form. This is stabilizing. Okay, so more bonds you form, more stable you are. I mean, the atoms are. All right. Maybe anyway. What questions, concerns, comments do we have at this moment? Any questions, concerns, comments? Okay. So now remember, this goes without saying. If bond forming is stabilizing, okay, what can you tell me about the bond breaking? It's destabilizing. Oh, why? It should be the other way around, the reverse of all these things. Due to bond breaking, the electrons get localized between the atoms. That increases the kinetic energy because electrons have less space to move around, and that increases the potential energy because there's more repulsions between the electrons. As a result of that, due to bond breaking requires energy. We need to provide energy to break bonds. Okay, so it requires energy to break bonds. So I want to mention here, if it is decrease in the total energy, this means this releases energy. Bond formation releases energy. Okay, so also just like that, it's a different sentence, but it's okay. Bond formation releases energy. Okay? If the total energy decreases, it has to be released. Okay. All right. Now, I'm not going to write about bond breaking. But you need to be able to justify. Okay. So this is for you to think about. Justify bond breaking absorbs energy, or bond breaking requires energy. Let's call it absorb. Bond breaking absorbs energy. Reverse of releasing. Okay. This is going to be, so how do we justify this? Is the reverse of all, what we talked about when it comes to bond formation. All right, that's it. We're done. Now we spent at least 10, 15 minutes on this. And then, you can expect a question from this page, like this page. Yeah. So why bond formation releases energy, or why bond formation is stabilizing? You can talk about it brings down kinetic energy, potential energy, and means it decreases the total energy. Therefore, it is stabilizing. Or that's why it releases energy. And if it asks about the other way around, bond breaking, you just talk about the reverse of these things. Done. Yeah. What questions, concerns, comments do we have at this moment? Anything? Any questions, concerns, comments? So I'm going to, I think I have a slide as well, summarizing, okay, maybe not, it's okay. All right, I will include a slide, next time. All right. Now, just for the bookkeeping purposes, I'm going to have this question open for you so that you can play with it. This next week's going to be Rusi.
Yeah.
Yep. And I think we have more than 90% responses. Therefore, I'm going to close this question in 5, 4, 3, 2, and 1. All right. And here are responses. Covalent bond formation decreases total energy, decreases potential energy, decreases kinetic energy, and so forth, which are the correct answers as well. All right. But you can see that even though we just talked about this, there are some people who are selecting other answers, only a small percentage. I think if you get off your phone a little bit, at least when you're, when I'm talking, it might be helpful. All right. Any questions, concerns, comments, anything? Yes.
What's the
Okay.
energy being released? Like, what is it?
Oh, yeah, it can be heat. So, Shed, your face told me something else. I'm sorry, I was wondering about. Yeah, so it can be heat in some reactions. So in some cases, it can be some other energy forms, but usually it is heat. So we say that bond forming is an exothermic process. Why? It releases energy to the environment. It heats up. Yeah. All right. Usually that's the case. Okay. Now, one other thing I want to actually point out, because you're going to see this in questions. Okay. Now, you have this simulation available to you on top hat. Now, look at this. This is hydrogen, right? When I bring the atoms, okay, so I can actually, this is where we have the bond. That's the minimum, okay? And it generated this form, this curve in the potential energy versus distance diagram. Oh, okay. So here we have the potential energy on the y-axis and the distance on the x-axis. Okay. When the atoms are far apart, you have like potential energy is almost zero, and when you bring them closer to each other, they're going to be potential energy will be negative. Why? They are attracted, and it's going to be a minimum at this point. But if you push the atoms even more close, okay, potential is going to increase even further. We have seen this before. Now, we can use this diagram. Can I increase the size of this? Maybe I can. Okay. I don't know how to go back there, but it's okay. Let's solve one problem at a time. Right. Now we can use this curve to determine the bond length. How do we do that? We know when the bond is formed, okay, it's going to have, at its optimum distance between the atoms, we have the minimum. So, and then on the x-axis, we have the distance, right? So if you read the x-axis value at the minimum point, that tells you the bond length. This tells you the bond length. Okay. You don't have the numbers here, but if you have the numbers, that is your bond length. Not only that, there's another piece of information that we can get from this. That is the bond strength. Okay. How do we get the bond strength? This is easy now because we know potential energy is a measure of the strength of attractive interactions. Stronger the attractive interactions, the lower the potential energy, right? So that means the y-axis value at the minimum, this point, this is the y-axis value at the minimum, tells us about the bond strength. Measure of, this is the measure of, let's say, measure of bond strength. Okay, I'm going to delete all of this. Okay. All right. So measure of bond strength. Without saying all that, we can say this. We say bond strength only. So bond length, bond and bond strength. So this is about the bond strength. All right. Okay. Now, if we use some other atoms, let's say carbon and carbon now. Okay. If I do the same thing, okay, I got this curve instead of that. So this is for carbon and carbon. All right, I made that curve. All right, this is for, let me use a different color for that. This is my CC bond. Okay, and the first one was HH bond. So the first one, this one is for HH. Now here's a question for you. Which bond is longer? Which bond is longer on your whiteboards? Which bond is longer? HH bond or CC bond? Based on the given information. Yeah, which one is the longer bond? HH. All right, whiteboards, please. Please, can you write your answer on the whiteboard? Oliver, I want the answer on the whiteboard. Okay, which bond is longer, CC bond or HH bond? Can you see a whiteboards, please, everybody? I want to see the whiteboards. Yeah. So I see. Do you guys have whiteboards? Okay, perfect. Thank you. Carbon-carbon bond. Yeah, almost everybody who showed me a whiteboard told me it's the carbon-carbon bond. Yes. How do we know that? The carbon-carbon bond minimum occurs around here. So the carbon-carbon bond minimum occurs here. Okay. So this is longer because it's x-axis, we are going to the right, right? This is longer than the HH bond length, which is occurring around here. Okay, it's about the distance reading from the x-axis. Which bond is stronger, HH or CC? Everybody. HH is stronger. Why? It has a lower minimum. It has once the bond is formed, the potential energy is lower for the HH bond compared to the CC bond. Therefore, HH bond is a stronger bond compared to the CC bond. Yeah. So that's how we read these diagrams, and then you might see them in your next homework assignment, and maybe exam as well. This is a nice question to have on the exam. If you, I mean, I can give you two diagrams like this, and then ask you which bond is stronger and which bond is longer, just like we did here. Yeah. All right. Any questions, concerns, comments at this point? Okay. If that is the case, I'm going to clear my doodling. I'm going to try to go back to. Okay, it's not that bad. We did this. Okay. Now let's move on to the main idea for today, main learning objective for today. Okay. Now we know the bond is held together by electrons. Okay. Bonding electrons specifically. Thing about the electrons is they are obnoxious. They move all the time. Okay. As a result of that, this given bond is not static. Okay. Because the electrons that is holding the bond together is moving all the time, the bond length changes all the time as well. And that causes the bond to vibrate. Okay. So if something is vibrating, we can talk about the vibration frequency and so forth. And on top of that, we saw previously this vibration energy levels, energy gaps falls within the IR radiation. Therefore, I mean, if we can, we can use IR radiation to induce vibrational motions in the molecule, to go from one vibrational mode to another vibrational mode. So this slide shows you some 4 types of vibrational modes. Okay, we can have symmetric stretching, anti-symmetric stretching, scissoring, rocking vibrations in molecules. Okay, so those are different modes of vibrations that have different energy levels. Okay, the energy gaps between them falls within the IR radiation, and that's why we can use IR radiation to induce vibrational motion in the molecules. Okay, so now another thing I want to mention right away here is, okay, IR radiation induces them. And Ella, this is what I meant by, different motions. So they have different energy levels. The IR radiation can induce them. Yeah, same thing goes with microwave radiation when it comes to rotations. All right. Now, another thing I want to mention here is I want to mention this, but I don't want you to take this that much seriously though. The equation part, but you need to understand what is meant by here. So the vibration frequency, like a spring, okay, bond is like a spring, right? So maybe in some physics 101 or something like that, you might have seen something along these lines. The vibration frequency, I'm going to say the frequency nu. We used that term before for frequency. I'm going to call this VIB, sub VIB for vibration. And so we know for a spring like this, the vibration frequency is given by something like, say, I think it's 1/2 pi, and then spring constant divided by the mass. Don't write this, please. Don't write this, okay? This is just to draw some parallels here. I just want you to see the relationship, okay? So this is for the spring. Just like that, we can relate this to the bonds as well. It turns out the vibrational frequency of a bond is directly proportional to the bond strength, which is analogous to the spring constant in our physics equation. Okay, we don't have to worry about the square root, but even though it might be there. Okay, and then it is inversely proportional to, this is kind of weird, but I want to tell you and then forget about it. The reduced mass. Reduced mass is Reduced mass involves both the masses of both atoms. Okay, and then it's m times m divided by m1 plus m2. But forget about that. Is directly inversely proportional to the masses of the atoms involved, just like m over here. Okay, now I'm gonna remove that. Okay, so higher the vibration frequency, we can it gives us an idea about the bond strength as well. When higher the vibration frequency, stronger that bond is. Okay, so for every given bond, they have their own bond strength and the masses of the atoms involved. Therefore, we can use the vibration frequency as a differentiating characteristic to identify that bond. Which is cool. Right. Anyway, I just want to mention that. So I just want you to have this idea. The vibration frequency is related to the bond strength and the masses of the atoms involved, especially the bond strength part. Okay, because we can do some problems with that. All right. Keeping that in mind, I will give you an idea about the IR spectrum. Okay, the IR spectrum. Actually, IR spectroscopists are really weird. Don't tell them I told this, okay? Right? And why? This is absorption spectroscopy. We could have easily have like absorbance on the y-axis and the wavelength on the x-axis. Instead, what did they do? They have a transmittance on the y-axis instead of absorbance, and then on the x-axis, instead of having the wavelength, guess what? They have 1 over wavelength. Why? Right? They could have easily had wavelength there. Anyway, it doesn't matter. It is still the wavelength. It's just 1 over wavelength. Okay. And then 1 over wavelength is known as the wave number. That's it. That is what is weird about the IR spectrum. Okay. So given IR spectrum have, inverted peaks like this because it's in the transmittance mode. And then each peak tells us about a different vibrational mode in the molecule. Okay, so for an example, we can use these peaks to identify the bonds in the molecule. For example, in this molecule, we have a peak at 1750 per centimeters. That's how you say that, by the way. Inverse centimeters is called per centimeters. Okay, once at 1750 per centimeters peak tells us that we have a C double bond O bond in this molecule. And also there are like multiple peaks telling us that there are CH bonds there in this molecule. Okay, so we have CH bonds and the C double bond O bonds, and that's all we have in formaldehyde. Okay, so now if you want to write something, I would write this. IR spectrum only tells us what types of bonds we have in a molecule. That's it. IR spectrum tells us what types of bonds we have in a molecule. Like whether we have a CO single bond, CO double bond, CH bond, CN bond, NH bond. IR spectrum should tell us that. That's it. Okay, you should write that down. Okay, now let's play with this. Remember, the x-axis is 1 over wavelength. Right? If if you're not sure, if your chances are 33.33%, I mean there's something missing. Okay, so keep that in mind. All right. Now we have closer to more than 80% responses now. Not closer, more than 80% responses. Actually, closer to 90%. Okay, I'm going to close this question in 5, 4, 3, 2, and 1. All right, and here are our responses. Okay. All right, so these are our answers. Most of us said CO stretching, and then not many of us said CH. Okay, and then some of us said O is stretching. Okay. Now, the correct answer here is CO stretching. Now, let's think about this. All right. Now, if you got this wrong, if you had a different way of thinking about this, please follow this. Okay. Now, there's nothing new here. We know energy of a photon is equal to hc over lambda, or hc times 1 over lambda. It's the same thing. Okay. Harshini, give me 1 minute. Okay. Then you can go back and talk to them one more time. Okay. All right. Now, please pay attention. So what I wrote was, what I've written on the screen is the same equation you have seen before, but I just separated the 1 over lambda from the rest. We know energy is equal to hc over lambda, and we know energy is inversely proportional to wavelength and all those stuff. Okay. What I did was I wrote it, in a slightly different way. Okay. We see that according the way I wrote that, we clearly see that energy is directly proportional to 1 over lambda, and we know 1 over lambda is the wave number. By the way, wave number, okay, yeah, let's call it wave number. Wave number. All right, let me say this. I mean, I just don't want to throw too many new things at you, but the wave number is usually denoted by the Greek letter nu with a hat. We call this tilde, nu tilde. It's not, nu is reserved for frequency, and then nu with a hat is nu tilde. Nu tilde is used for the wave number. But anyway, it's just for extra information, okay? Anyway, so we say that energy is directly proportional to wave number. Right? And then we see that out of all the peaks, CO stretching has the lowest wave number. Therefore, it requires the lowest energy. That's it. Done. That's all the thinking we need there. To understand that energy is directly proportional to the wave number, which is coming from the equation we are already familiar with. Okay, because CO stretching has the lowest wave number, that must take the lowest energy photon. That is it. Any questions, concerns, comments at this moment? Okay. Now, I'm not going to do this today, but I'm going to give you a preview of coming attractions, but I'm not done. I'm going to, go to the next one. We can calculate the energy of this photon, by the way. And let me reopen this as well for the people who want to revise the answers. So we can calculate the energy of this lowest energy transition. All right. And then how do we do that? Let me get you started, because you already know how to do this. Okay. So energy of this photon is given by none other than energy is equal to hc over lambda. This is the only equation we use. And then we were given, we know h, we know c. Even though we are not given lambda, we know 1 over lambda is 1000, right? 1000 per centimeters. We know that. Meaning we know lambda. If 1 over lambda is 1000, what is lambda? If 1 over lambda is 1000, what is lambda? 1 over 1000, thank you. 1 over 1000 centimeters is our lambda. And then we want this in meters. We know how to convert centimeters to meters. Okay, we're gonna multiply this by 10 to the power of -2, because that's how many meters we have in a centimeter. Centimeters cancel out. We are going to get 10 to the power of -5 meters as our wavelength. And now what do we do with this? We take that to our equation, and is equal to h is 6.626 times 10 to the power of -34 joules seconds. I don't know why I remembered that. All right, weird. And then c is the speed of light, 3 times 10 to the power of 8 meters per second. I try to forget about these things. And then divide this by the wavelength, which is 10 to the power of -5 meters. Seconds cancel out, meters cancel out, and you're gonna get the energy in joules. I wasn't planning on doing this, but anyway, so if I do this, this should be 10 to the power of negative 29. And then 3 times 6.629 should be 19.8 something times 10 to the power of negative 21. And then if you rearrange this to scientific notation, it should be 1.98 times 10 to the power of negative 20 joules should be your answer of this photon. I'm sorry, I wasn't planning on doing this. I wanted you to do it, but anyway, I got carried away. So the idea is you can calculate the energy of the photon, using the wave number, starting with the wave number. That is the whole point. Okay. So any questions, concerns, comments at this point? All right. You can convert this to kilojoules per mole. That should be your homework. Okay. And then all right. Let's do maybe two more things. All right. So I made you write a note about IR spectra. Just before we talked about the lowest energy peak. Okay. This is about whether you wrote that and then whether you really mean it when you wrote it. Okay. All right. So we have closer to 90% responses. Therefore, I'm going to close this question in 5, 4, 3, 2, and 1. Okay. And then here are our responses. The correct answer is okay. Now I know whenever the answer is need more information, it sounds like a trick question, but yes. Okay. Now, but it won't be a trick question if you meant what you wrote. Hopefully you wrote that. Okay. You wrote in your notes. Remember what I asked you to write? I asked you to write that IR spectra tell us what types of bonds we have in the molecule. That's it. Did I tell you that it tells us how many bonds we have in a molecule? No, it only tells us, okay, what types of bonds we have in a molecule. So according to this IR spectrum, only thing that we know is in this molecule, we have at least one CH bond, one CO bond, and one OH bond, at least. But it doesn't tell us how many we have. Okay. And this bending and stretching are two different modes of the same bond vibration. These are two different modes of the same bond. Okay. So it doesn't mean that that's because it is mentioned twice. It doesn't mean that, it has two of that. All right. I'll reopen that. Okay. Any questions, concerns, comments? Let's do this. Now, you can imagine how these questions are going to go. I mean, looking at these questions, usually you can be given the mass spectrum, and then, that tells you the molar mass of the molecule and what fragments we have and stuff like that. And then you can be given the IR spectrum, which tells you what bonds we have so that we can build the molecule. That's the idea there. Okay. Now, before I look at your answers, I'm going to show you the way I approach this. Okay. So mass spectrum is kind of useless here. Why? All of them have the same mass. All of them have the same number and types of atoms. Therefore, it doesn't play any role. But there will be situations where the mass spectrum is useful to determine the molar mass and to eliminate some, wrong options. Okay. Anyway, so in the IR spectrum, we see that we have CH bonds, OH bonds, and the CO bonds. Okay. So in molecule 1, we have CH, we have OH, and then we have C double bond though, not CO. There's no CO bonds here. Therefore, 1 is out. And option 2 is out for the same reason. We see that we have C double bond O, which we do not have in the IR spectrum. If it is not in the IR spectrum, it does not have any business being in the molecule, and vice versa. Okay? And then molecule 3 has C double bond H bonds, which is not in the IR spectrum. And also, there's never a case that hydrogen can have more than one bond, unless you're from ASU. They do weird things. All right, anyway, so that is out. And that leaves us option 4 as the answer, where we have CH bonds, CO bonds, and OH bonds. Okay, the alpha correct answer is option 4. So most of you got there, but I'll reopen that. So when we come back on Tuesday, this is what we're going to do. Just a preview. I have 1 more minute at least. Okay. So you know what? Never mind. Let's talk about it on Tuesday. All right. All right. Bye, everybody. See you Tuesday.
Thank you. Have a good.
You too. Hi.
My